Hello friends, in today's question, two identical ladders are arranged as shown in figure. Mass of each ladder is m and length is L. The system is in equilibrium. Find the direction and magnitude of frictional force acting at A or B. So this is a diagram. A and B are inclined at an angle of theta and they have a common point P and a mass of small m is hanged from this point P. Length of each ladder is given as L. So more or less for both A and B everything will be same because they are just mirror image of each other. There will be minor difference between the forces which will be acting at A as well as B. So let us draw the free body diagram for A first, then for B, and say for letter A, angle theta, this is point A and this is point P, and there is frictional force, let us suppose Fr, and the normal because of this contact, let us call this as N. The downward direction, there will be a force, weight rather, mg, and you can say as the point, this mass is hanged at the middle of point P, or rather ladders, so we can divide this mass equally for letter A as well as letter B. So here for letter A, this will be equal to mg divided by 2, and because of the contact forces of ladder A and ladder B at point P, there will be a normal direction in this direction, and we can divide into two components. Let us call these components as N1 and N2. Okay. So these are the forces which is acting on ladder A. Similarly, we can draw for ladder B. So this is our ladder B, angle is theta, B, and this is point P, and here also in downward direction there will be mg, and this is the second equivalent part of small mass m, mg by 2, a frictional force Fr, there will be a normal N, and in this case there will be a normal because of rod A acting this direction, so it can be divided into two components. So this will be our N1, and here in the downward direction there will be N2. So these are the forces. So let us write one by one what's the meaning of all these forces. So you can say that this normal at point A and B the normal N acting at point of contact for A and B. The second, N1 is the horizontal component and N2 is the vertical component. You can say N1 is a horizontal component of normal reaction at point P between the two letters. And similarly N2, that will be vertical component. N2, the vertical component of normal reaction at point P between the two letters. Next is regarding the weight which is hanging from point P. You can say both ladders will share the weight mg. Therefore, let's say mg by 2 will be weight for each ladder. Next is our frictional force Fr. Fr is the frictional force. So these are all the forces, and it's given that the system is in equilibrium. You can say as the ladder is in equilibrium, the net torque as well as the net force will equal 0. So you can say net torque, which is tau net, equal to 0. Net force let us call this F net, will also equal 0. And along with this, the summation of forces in x direction and y direction will be respectively equal to 0. Now the torque will be because of the friction and because of normal, which will be acting in the opposite direction, so they will try to twist the ladder. Okay. So we can consider any one of the ladder A or B and try to solve it because they are almost mirror image of each other. So let us start with ladder B. You can say for ladder B, let us consider all the vertical forces for vertical direction. So in the upward we have N force, and in downward we have N2, mg by 2 and mg. So we can say that N will be equal to mg by 2 plus capital Mg and then it's N2. Let us call this equation 1. And for horizontal direction, there is only one force, that is friction Fr and the normal N1. You can say Fr is equal to N1. Now next we are going to consider for ladder A Similarly, we can write the equation. In this case, in the upward there are two forces, N2 and N1, and in the downward direction we have mg and mg by 2. So we can write this as N plus N2 is equal to mg plus mg by 2, and this is for vertical direction. Let us call this equation number 2. And for horizontal, we can say that our Fr will be equal to N1. So we are going to use equation 1 and equation 2. Using equation 1 and equation 2. From equation 1 we find out our N2, we get this as N minus mg by 2 and minus mg, and from equation 2 we get N2 is equal to mg plus mg by 2 minus n. This comes mg plus mg by 2, and this will be equal to minus n. Okay, so from equation, therefore we can write that n minus mg by 2 minus mg is equal to mg plus mg by 2 minus of n, and from here we can say this will be 2n. So we get 2n is equal to, this will be 2 mg and this will be 2 mg by 2. So this 2 cancels out throughout, and we get this normal as mg plus mg by 2. Now we consider for rotational equilibrium, we can say the net torque should be equal to 0. Okay, for rotational equilibrium, net torque that is tau net should be equal to 0. So let us consider for ladder B or ladder B, the tau net should be equal to 0. And in this case, we are going to take that in case of anticlockwise direction, the torque is taken as positive, considering anticlockwise rotation for torque as positive. Therefore, we can use the general formula for torque, which states that tau should be equal to force multiplied by perpendicular distance. Okay. Now, there are some of the forces which passes through the reference point O. Okay. So you can say forces N1, N2 and mg/2. So these forces N1, N2 and mg/2 passing through reference point this, that is P, and therefore their torque about this point will be 0. So forces N1, N2, mg/2 pass through reference point P. Therefore, the torque about the torque will be 0. Now let us draw all the relative perpendicular distances and solve it. So this is our rod B. B is point P, and this mg will be in diagonal direction, and the total length is given as L, so this distance will be L/2. And here we are going to have mg/2 and N2, and in this direction we are going to have N1 so we can say this total distance will be L cos of theta, because total length is given as L, and this distance, because this is theta, so we are going to have this L sine of theta. Therefore, now we can use the relation that it will be 0 at point P. So let's write the equation. Therefore, the equation of torque about point P, so we get this equation as minus mg, and this distance will be L/2 cos of theta, we get this as L by 2 cos of theta, and minus, we have frictional force here, Fr, and it is a distance L sine theta. So we get minus L, sorry, Fr multiplied by L sine of theta, and there will be normal which will be acting in upward direction here. So we get this as plus n, and which is a distance of L cos theta is equal to 0. So here L cancels out throughout, so we get this as minus mg cos of theta divided by 2 minus Fr sine of theta plus n cos of theta is equal to 0. But we calculated the value of n. So the value of n is mg plus mg by 2, you can say, but n is equal to mg plus mg by 2. We are substituting this equation. We get this as mg by 2 cos of theta plus Fr sine of theta, and our normal was mg plus mg by 2 cos of theta. From here we are going to find out our f for sine theta. F for sine theta is equal to, we open the bracket, this comes mg cos of theta plus mg by 2 cos of theta, and this will be minus mg cos of theta divided by 2. So we can solve these two terms. We get this as Fr sine of theta, so this will be 2, and mg cos of theta, we can take g cos of theta common, so this becomes m plus m divided by 2, and this will be g cos of theta. So finally we get friction is equal to m plus small m divided by 2, and g, this will be cot of theta. This is the magnitude of the frictional force acting at A or B. This is the magnitude of frictional force acting at B, and it will be same at A also, because Fr is same in both the cases, and direction we have already shown in the figure. You already know it will be towards away from B as well as away from A. Direction will be towards each other. If it's B, it will toward A, and if it's A, it will toward B. So this completes the question. Thank you.